So we've been talking about accumulating volume using an integration over the last several days in lecture. Obviously, it's a tricky concept. It's a lot of moving parts to keep track of, a lot of different things to keep track of. So I want to say this before we get going here. Ask me whatever questions you have. I mean, I have quite a bit to get through, but there's also plenty of time for you all to ask me questions. Please do that. So like I said, we're gonna be talking about accumulation of volume using integration to do that. Just to kind of get you all in the right frame of mind. We've got a couple of things for y'all to work on. So I'm going to share my screen, have you work on a few things, and then I'll be back with you in about 3 minutes here. Can you see what I'm sharing?
We can.
Okay, good. All right. Go for it. I'll check on you in just a bit.
So I'm having a little bit of trouble conceptualizing this. So
Okay.
when you say empty shell, are we overlapping like the shape once we turn it a certain direction, or?
Basically, when you revolve it around any given axis, it's going to revolve, and then it's going to revolve a full rotation and sort of land back on itself.
Okay, so it doesn't necessarily have to be like a perfect image within itself. It's just going to be a little.
No, I mean, there might not be a geometric way to describe what results. Yeah. That's fine. Anybody need another minute or so, or can we take a look at these? All right, I'm gonna go ahead and stop sharing so I can share from my tablet. Okay. Can you all see this?
Yes.
Good. All right, so first thing we're gonna do is revolve this shape around its left edge. So let's use orange. First thing I want to do is just really darken in this edge where I'm going to do basically that's my axis of rotation. And just lightly shade in this two-dimensional region that we're going to rotate. So I think the easiest way for me to visualize what's going to happen when we rotate this is to first do just a reflection. So I'm just going to kind of reflect this, make a mirror image of this across that orange line and sort of fill in some of the details. You'll rotate it so you'll see that the top of the shape is going to become circular. So will the bottom of it. So you sort of have this lampshade looking configuration here. Any questions about how I've done that so far? Okay, so let's move on to the next one. So again, just shade in that top, or fill in that, darken the axis, shade in the shape again. And again, this is just to kind of give you all a, make sure we're in the right frame of mind of, so yes, I can easily envision a graph in 2 dimensions on a flat piece of paper, but what does it look like when I'm going to revolve that? So again, I'm going to have a reflection. So you see kind of on the left-hand side of the y-axis here, we have this cylinder, and on the right-hand side, you see a cone. So the one we're going to spend the most, sorry, was there a question?
No, that makes more sense. So you're saying like if it kept that shape, it would be 3-dimensional?
Yeah, absolutely.
Oh,
And that's what makes this inherently hard to visualize. We have flat surfaces and we're trying to draw 3-dimensional objects on them. It becomes hard to visualize. The one that we're going to spend the most time on today is revolving this image around the bottom edge. So when you were trying this, it probably was more obvious that you needed to revolve around this edge. You may not have consciously known that you were revolving around that edge as well, but everything on that bottom edge. So again, just reflect this is easier for me to look at it in terms of left and right. So if I reflect that, you're going to have, again, another cylinder. This right-hand region is going to be a little harder to represent, but if you can imagine that this is also going to be cylindrical in shape, but it's going to have a cone removed from the very top of it, from the very right-hand side of it. So this is the object that we're going to spend this period finding the volume of, is when we take this shape, this graph, and revolve it around its bottom edge. So before I go too much further, I just want to make sure, are we visualizing this decently? I don't want to say perfectly because I don't think anyone's there. But does anybody have any questions about how we've constructed this, or how we're going to construct this strange solid? All right. So again, I can't stress this enough. This is inherently difficult stuff. And it's not just for you all, for anybody. I just started a PhD program here, but I have vivid memories of having difficulty understanding this the first couple of times I saw it. So please ask me questions that I know some of you have. So the first thing we're going to do is vary this through the x-axis. So before we do that, let's just chop up our graph here into these arbitrarily wide delta x intervals. And for this one, I'm going to do a couple of them. So let's do a delta x there. And what I like to do in a couple of different colors here, let's do light blue just to shade in the whole region. And then in a darker blue, I am going to just take one little strip here. Now, instead of revolving this entire thing, I'm just going to revolve this one thin strip. So if I were to revolve that around the x-axis, what kind of shape am I making here? Basically, I took what was a rectangle and I wrapped this around an x-axis in a circular fashion. What shape did I end up making?
A cylinder.
That's going to be a cylinder. So I remember, kind of thinking back to the way that Mark has talked about this. When you're finding volumes, really everything we found a volume of is really just cylinders. That's the only real shape we need to think about. So let's look at another dx interval here, because we can see that if you look to the right of the x-axis, this is going to behave a different way. So now I'm just going to make a strip here, but we're going to use the left end approach just to keep that rate of change constant over that interval. So now I'm going to draw this in. Now, before I revolve this, what kind of shape do we think this is going to become here?
Something like we saw in our example on Friday.
Okay. Can you describe that for me? Like what shape is that? Or can you describe that using?
He said, like, I think a shell, like a cylinder with a shell, or that is a shell.
Okay. David says donut in the chat. It's a good explanation. So basically, let's just do this. If I revolve that top edge, the one that's furthest away from the x-axis, if I were to fill that whole thing in, hopefully you can see or can convince yourself that if I were to fill in that whole shape, it would be no different than the one I already drew here. But because the strip that I'm revolving around the x-axis does not reach the x-axis, it's going to have a hole in it. Now, what shape is that hole that's going to be punched out of this? So let me back up a step. If I were to color this whole thing in, the entire thing, what shape would that be?
A ring?
A ring? Give me a more precise geometric term for so remember, right now I'm just acting as if there is no hole in it. It's completely solid.
Another cylinder.
That'd be a cylinder, right? So it's a ring because it has a hole in it. What shape is that hole?
Is it cylindrical?
It's cylindrical as well. So let's back up. Let's back to 2 dimensions for a second here. This right here that I revolved around the x-axis, this was a rectangle. But this negative space here that wasn't quite as obvious that I revolved around the x-axis, that's also a rectangle. So the blue over here, since that reached all the way to the x-axis, there was not going to be no hole in it. That's going to make a solid cylinder. This one here is going to make basically a cylinder with the cylinder removed from the center of it. Basically, both those cylinders share the same center, but you can't find the area or the volume of that. You can't find the surface area or the volume of that cylinder in a straightforward way like you can this one on the left. I think that's a good place to stop and make sure people get their questions answered if they have them. How are we doing with just like, haven't really done anything quantifiable yet. We're just visualizing what's happening. Any questions so far?
Makes sense.
Okay, good. So what variable did we say we were going to use to integrate on for this approach? X or Y? Look at my intervals. Are my intervals in X or are they in Y?
X.
They're in X. So we should probably back up a little bit here. We're basically doing one key thing here. We're finding the volume of a cylinder. How do you find the volume of a cylinder?
of circle times height.
Okay, so I got the area of a circle times the height. Now we can break that down a little more. How do you find the area of a circle?
Pi r squared.
R squared. So a volume of a cylinder is going to be pi times radius squared times height. So basically, a cylinder, to really describe it or to find its volume, you need to know two dimensions of it. You need to know its radius and you need to know its height. So look at our cylinders here, the ones that we've swept out and revolved. As x changes, so as I start from the left and move towards the right, what is changing? Is it going to be the height or is it going to be the radius?
Height.
It's going to be the height. So as x increases, height increases. And that's important to know because let's just visualize this shape on the left here. As I'm varying x to the right, you can think of me adding the area. So the way I'm adding volume is just by adding these circular sheets to the right end of that graph as I vary from left to right. So one key thing to keep in mind here is that, I don't care what kind of accumulation you're doing. If you want to know how much you're accumulating, in this case, we're talking about volume, you need to know a rate of change of that volume. So a rate of change of a volume, we always need to be looking at an area. So rate of change of volume is area. But now we have to figure out what area we're talking about. So we're moving to the right and I'm adding, now let's just talk about, I'm back at area, so let's talk two dimensions. What shape is that area being added in? As I'm moving to the right, what shape is the face of a cylinder where I'm adding all that area?
A circle.
It's a circle, right? So that means for us, the rate of change in the volume is going to be the area of a circle. Now, on the left-hand side here, that's a little easier to think about because it's a circle. It's just a simple circle. This one over here is a little more complicated because I have a circle with a smaller circle removed from the center of it. So one thing to think about here, let's look at this head on. If I have a circle here, pretend that's round. Oh, yikes. Let's just freehand it. So how would I find the area? How would I find this black area here?
You would take the height of the top line
Okay.
and use that in the area of a circle, right?
Okay, so find the area of, it sounds like you're saying find the area of the entire circle, right?
Yes, at first.
Okay. All right, keep on going with that. What would you do next?
Well, and then since like the middle varies, I would just take like at every given point, however you represent that functionally, at every point along the slanted line, that would be like the area of your inner circle, or you'd use that height.
All right.
Inner circle.
So I'm going to back it up, and for right now, let's make it a little simpler. Let's just this circle right here. Let's just assume that everything is constant. Those two radii are constant. So basically, you would find the area of the larger circle and the area of the smaller circle, and just find the difference between them.
Mm-hmm.
So then, if we think about that, we can extend this to 3 dimensions. So this one right here assumes that I have one radius. It's solid. There is no circle removed from the center. This one right here accounts for the fact that there might be. Before I go too much further, do we understand the notation of the capital R squared and the lowercase r squared? Something else I've seen people do is pi RO squared for outer radius.
I'm a little confused about that. What is the difference between the upper and lower case?
Sure. So basically we use uppercase to show that one is larger than the other. So this circle right here, this radius out here, that would be capital R, and this one here would be lowercase r. So to really find the area of that circle, I need to find the area using the larger radius. I also need to find the area using the smaller radius, and then subtract the smaller from the larger. That answer your question?
Yes, thank you.
Good, no problem. All right, so like we said, the reason we're doing this is because the rate of change of volume is the area of a circle. So now we're going to use this here. We have the area is equal to pi times outer radius squared minus pi times the inner radius squared. And before we go any further, this is a good place to stop and make sure we're all doing all right. Does anybody have any questions? Or it's really important that you know why this is being used. If you're not okay with that, please ask me to clear something up for you.
So that area function is the area of like the ring that we're getting, like the base of it, right? Or no?
Yeah, that's the area. That's exactly it. That's the area of, if you were to look at the, if you were standing here looking right at the face, if you're standing there, you don't see a cylinder, you see some circular ring.
Mm-hmm. Okay.
Yeah, we're just looking at that area of that face, of the leading face.
Gotcha. Sorry, I need to talk things out. So
Oh, I'm fine. I'm glad you are. So from here, basically we're going to try to figure out functions in X for both of these. But before you can do that, I need to tell you what functions are happening here. So I have 4 different equations. Shouldn't call them all functions. So y equals 2x, that's going to be this slanted line right of the y-axis. Y equals 2 is the top edge. Y equals 0 is going to be the bottom edge. And x equals -3 is going to be the left edge. So that's how we're bounding this. Oh, actually, one more thing we need to do. So we're looking at our area function here. Like I said, there are 2 dimensions that tell you how to find the volume of a cylinder or what a cylinder looks like, a radius and height. The only one that showed up in our rate of change function was radius. So let's ask this. First of all, does the radius come from a y value or an x value?
Y.
Comes from a y value, right? So now next thing we need to worry about is, can I use the y value as is, or do we have to adjust it for something? For example, right here, let's say y is equal to 1. Does that mean the radius is 1? Or if we look at the full thing, this is going to be y equals 2. If y equals 2, does that mean the radius is equal to 2?
Yes.
Yes. So we can just take the y value as is. Similarly over here, your inner and outer radii are just going to be those y values. So as I mentioned before, depending on whether you're on the left or the right-hand side of the y-axis, you're going to have a different behavior. So let's look at the behavior on the left first. And because they have different behavior, we're going to have to define a piecewise function. So first, let's do this. Let's define this function for minimum value of x all the way up to the y-axis. So what's our minimum value of x based on the equations I've given you that bound this region? Banks is -3. We'll go with that.
Nice.
We understand why that's the case. I gave it to you. So basically that's as far left as this thing goes. And for this first piece of this piecewise function, how far to the right am I going to go?
3.
Not 3, because remember, when I get to the y-axis, I have to use a different definition because of this cusp right here.
0.
I'm going to use 0. So the important thing to keep an eye on is this. The area is equal to pi capital R squared minus pi lowercase r squared. The nice thing about the function, the way this behaves on the left, is that there is really no inner radius to speak of. It's just the outer radius. What is the outer radius on the left-hand side of this region?
2.
It's a constant 2. So my function here is going to be pi times r squared. Any questions for that?
Could you write next to the bound regions like what they represent, just so I can remember?
Yeah, sure.
Sorry, it would just help with following along.
No, you're good. So I think this is what you mean. This is the left. Is this what you're asking for, Robert?
Yeah, it's
Okay, good. And then this one, how can I describe that? Slanted bottom?
Oh, okay. Yeah, that was simple. Oh my gosh. Okay.
Okay, you see it now?
Yeah.
Essentially, if I were to ask you to graph those 4 functions, no, I shouldn't say functions, those 4 equations, those 4 lines, it would probably jump out at you. You know, you would have lines going off in many different directions, but hopefully it would be clear that there is a polygon, there is a region that is enclosed by all of them. That's a good question though. All right, so for the second one, definitely starting at 0. How far to the right am I going? So essentially, how far to the right is this point here that I just circled in the graph?
About 4
Where'd you get 4?
from the points on the graph below it.
Okay, so remember, I just drew those intervals kind of haphazardly. This thing isn't to scale by any means. So you can't really go off the hash marks I made. How else might we take this on?
Wouldn't it be where y equals 2 and y equals 2x intersect?
That's
So
exactly it.
just 1.
Yep. So I see a lot of people chiming in the chat as well, seconding this. So because I know that 2x, so basically that's going to be the intersection of the slanted bottom and the top. So I just set those 2 expressions equal to each other, which gives me x equals 1. So that defines that interval, 0 to 1. So now in that region, I will have an outer radius and I will have an inner radius. So I'm going to have to do both here. What's the outer radius on that right-hand side?
Still 2.
Still 2. Except now, the only difference between these two is that I have an inner radius. The outer radius didn't change. What is the inner radius?
1.
Not 1, because remember, it's only 1 at the very end. Actually, it's not 1 at the very end. That's just the x value where this ends. So now I have to figure out what the inner radius is going to be anywhere. I have to generalize it. So we said this right here was the point 1, 2. Let's say this point right here is actually, Let me delete some of these things so I can see what I'm doing. Let's see, this point right here is 1/2, 1. How would I generalize the inner radius there? And I see in the chat from Bang, it's gonna be 2x. So basically, given any x value on this graph on the right-hand side, I can find the inner radius from this equation by doubling it. Basically, 2x gives me that y value. So this right here is the most important thing to find the volume. I have fully defined the rate of change function that I can use to find the volume here. Any questions about how we got this thing?
Could you explain again how you got 2x for the inner radius? I'm sorry.
Sure. So you're good on the outer radius?
Yes.
Okay, so let me draw that strip back in that I made, or maybe let's make a new one. So let's say I want to do this one right here. Color it in, and we're going to do this cylindrical cylinder with a hole in it. The outer radius is clearly 2, right? It never changes. The outer radius is constant. But depending on how far left and right I move, it changes the inner radius. Basically, it changes that cylinder that I have to find the volume of and subtract off. And the radius of that cylinder it's totally given by that y equals 2x function. So basically, we said a while ago that the radius was a y value, right? This y value at the top is y equals 2. And this y value at the bottom here is y equals 2x. So basically, if we look at the equation we made, I have pi times outer y squared minus pi times inner y squared.
I understand. Thank you.
Good, no problem. Good questions. Now from here, we're going to use this to build the volume function. How do I get from my area rate of my rate of change function to the volume? What operation do you know that I have to do?
Integrate.
Got to be an integral, right? What's the lower limit of that integral going to be? Where do I want to start accumulating volume?
-3.
-3. And for now, let's just keep it general. I want to accumulate volume for any x value. So given that, what am I integrating?
Rate of change function.
Okay, what did I call that rate of change function?
Area.
Right, so it's just one here. So I'm going to call it a of t dt. And that's basically it. That is your integral to find the volume using this approach. Any questions so far?
I appreciate this so much.
Good, I'm glad to hear it. Like I said, I mean, this is one of those things that I feel like you have to see it a bunch of times and think about it. It's not easy by any means.
Oh, could I actually just get the area integral
Yep.
really quickly? Oh, okay, I'm good.
So I'm going to leave that while I do our next approach here. So now we're going to find the same volume, but we're going to vary it through y intervals. So now I'm going to chop this up into delta y intervals. Let's go back to blue. Shade in the region we care about. And we'll use a darker strip So now if I were to revolve this, I'm going to get a cylinder, right? So like I said, I mean, we're still dealing with cylinders. In this case, I'm no longer going to have x be the variable that I integrate on. I'm going to have y be the variable. So I'll ask you this question. As y increases, what increases? So just to remind you, we said this about the volume of a cylinder, pi r squared h. So we have two dimensions that govern cylinders, basically. As y increases, which of those increases with it? Radius or height?
Radius.
Radius this time. All right, from there, so now we have to think about what area is increasing as y increases. So remember, for the x, when we were varying through x, it was the circular face on the right end of this cylinder. That's not going to be the case here. Now it's going to be, this face, which I believe Mark calls the lateral surface. Term I usually use is the curved surface. A cylinder has three faces: two flat ones, the two circular bases, and one that's curved. So basically, now that we're making small dy changes in y, the metaphor I used for my last class was basically you're putting toilet paper on the roll. Basically, you're adding thin cylindrical sheets to that shell to accumulate volume. So having said that, our rate of change is the area of the curved surface. How do we find the area of that curved surface?
2 pi RH.
Right, good, 2 pi RH. And this is a little harder to see, but if you were to basically unspool this, you would have a rectangle where the radius would be this dimension, this width, and 2 pi h, the circumference, would give you the length. So that's our rate of change function. Area equals 2 pi RH.
So is that the surface of the, is that the entire curved surface, or are we working with like a splice of it?
No, so here's what I did here to get from the blue cylinder to this. Imagine if you could take off a layer. I'll go back to the toilet paper analogy, or a paper towel, whatever you'd like.
Okay.
Your paper towel roll is clearly a cylinder, but you can definitely remove rectangular sheets from it, right? So
Yeah.
just envision taking off that top layer and unrolling it. It's going to make
Okay, so like one full layer.
Yeah, basically that's what that
Okay,
is.
okay.
That's why this dimension is 2 pi h. It is the same as the circumference of the base of that cylinder.
Okay. I was just confused if we were taking a segment. I was like,
Nope, sorry, no, that was a full
Yeah.
layer.
Thanks.
Good question. So our area is equal to 2 pi RH, and our job now is we want to get r in terms of y, and we want to get height in terms of y, because that's the variable we're going to end up having to integrate over. So you all said before that the radius is given by y value. That's the same here. How about the height? Is the height related to the x value, or is it related to the y value?
The x value.
Good. But one thing to be careful of here, right here, x is equal to 0. Does that mean the height at that point is equal to 0?
No, because there's a difference in it.
Right. So the radius is given purely by the y value. The height is going to be given by x value plus 3. Because basically, this really does start at that vertical line, 3 units to the left of the y-axis. So we have to make that adjustment. But we can use that idea to start building up our rate of change function. So we have area equals 2 pi RH. We said that radius is given purely by y. And we said that height is given by x plus 3. Now, what would be the problem with this if I tried to integrate it the way it's written?
You can't integrate the x.
Right. So what variable do I have to have this whole thing written in terms of to integrate?
Why?
Right. Our goal is to get this thing represented in y. So is there a way I can represent that x in terms of y? Do we know anything about how x and y are related here?
Y divided by 2.
Yeah, so we know that y is equal to 2x, that was given. So I can rearrange and get that x is equal to y over 2. So now I feel good about making my full rate of change function 2 pi times y over 2 plus 3. Any questions on where this thing comes from?
Could you go over why the height is x plus 3? Or the
Sure.
height, yeah.
So let's look back at it. Actually, maybe it'd be better if I went, no, I don't have any 2D pictures anymore. That's okay. So look at this blue cylinder we drew here. Let's try this x equals 0. Let's say the cylinder was cut off. Let's use a different color for this. Let's say that I just cut this cylinder off right here. So where it went from, the same left end as the other one, but it only went as far as the y-axis. What is the height of that red cylinder right there?
Three.
That's 3. What if I went 1 unit further? Oh no, the whole thing is. So if I went 1 unit further, that height would be 4, but the x value would be 1. Let's go in reverse this time. If I had this cylinder here, and I called this point x equals -2, what would the height of that cylinder be? Remember, it starts at x equals -3. So
1.
it would just be 1, yeah. So basically what you're doing is this. You're taking your x final minus your x initial. The x final is really y over 2 because the x final is going to be wherever you hit this slanted surface. The x initial is always going to be -3. So cancel out the negatives, you're going to get y over 2 plus 3.
That makes sense. Thank you.
Good. All right, our last thing to do here. Like I said, finding the finding the area rate of change function is the most important thing. How do you get to the volume once you have this function? Again, what operator do you know that I have to use?
Integral.
Integral? All right, give me limits for this integral. Remember, we're in y this time, so what's the least value? What's the lower limit of this integral going to be?
0.
It's going to be 0.
Okay.
And the upper limit will be what?
2.
2. And Just like last time, our integral is going to be a of t dt. Actually, did we keep the other one general? Yeah. So instead of calling 2 would give you the entire volume. But what if I just wanted some volume, some general volume, anywhere between 0 and 2? That function right there would give me the volume at any point. Any questions, guys? All right, if there are no questions, I am going to go to Canvas, and the quiz is already open because you all are the last recitation of the day, but I need to give you the password, so I am going to find it and post it in the chat. Anybody have any last minute questions for me? All right, let me go ahead and find that password, and then I will get it over to you. All right, passwords in the chat. I'm going to stay in the room for a few minutes if anybody has any questions or any problems with Canvas. Otherwise, thank you all for the good questions. I will see you all in lecture or office hours. Have a good day, everyone.
Thank you.
Thank you.
Also, I was just wondering if you were to take a strip at the last y value or delta y value up to 2 and then rotate it around the x-axis, it would have that cone taken out of it, right?
Right, so the one thing to keep in mind is remember, you're not taking that whole cylinder's volume, you're taking the volume added just from that thin little sheet you made. So with every like little tiny dy, you're just accumulating a little bit of volume. So really, you're adding a hollow shell.
Okay.
But yes,
Thank you.
as you integrate over the full interval, it's going to have that cone taken off.
Okay. Thank you.
Good question. Thank you.
Could I actually ask you if I could reword this differently? Just not answer, but like if it could be reworded. You could say yes or no once I say it.
Sure.
Okay. If it says accumulating the volume of an empty shell is the value of y varies through change of y intervals, does that mean the height is changing?
Not necessarily.
Okay. Okay.
So just when we say y, we're talking purely the vertical axis on our graph,
Gotcha.
which may or may not be the height.
Mhm. Thank you. Have a great day.
Mr. Professor Ruiz, can we go over them right now? If it's just us two. I think you're muted.
All right, sorry about that. So, question 1: if the radius of a typical cylinder is varying in the current delta x interval, then the rate of change of the volume is. So that was the first example we did.
Yeah.
So remember, it's all about what face.
The area of the base, right?
Yeah, the area of the base.
So I chose pi r outer radius squared minus the pi r inner
Yep.
squared, right? Okay.
Yep.
So I did that. So the second one, what was the question?
If we were accumulating the volume of an empty shell as the value of y varies, okay, what is the input variable of our volume accumulation function?
Volume. So input variable. I put h.
So it's actually y.
Okay, that's okay. I narrowed it down to those two, but
Yeah.
what I thought was like, you know how we plugged in the radius for like
Mhm.
for the first one, then we plugged in for the height for the second one.
Right. But so again, my radius and height are 2 dimensions of a cylinder, but
Yeah.
we still boiled them both down to the variable we actually cared about.
Okay.
So for that question too, if we're dealing with delta y intervals, then y is the variable that we're integrating over. So y is going to be that independent variable.
Okay.
H is actually not a variable in this equation. I mean, it's
No,
how we define other things, but
I completely misunderstood the thing.
gotcha.
The last one was oh yeah, the intervals. It was the integrals for like -3 to 1, right?
Yeah.
And to find the volume of the whole thing, I put 1, right?
Yeah, it's v of 1. Because remember, our volume function had built into it, the lower limit was -3.
Wait, the answer is v of 1?
Yeah.
Okay, I think I got 1 out of 3, but I only got the second one wrong.
Oh.
I don't know.
Let me look at number 1 again.
Can you see them? Oh.
Yeah, I'm looking at them. Oh, you know what? It says typical cylinder. Okay, so if it's a typical cylinder, it has no inner radius. So the answer to that one should be pi r squared.
So what was the answer to that one?
The first one's pi r squared.
Pi r squared.
Because if it's a typical cylinder, it has no missing hole in the middle.
Yeah.
Okay.
Okay.
Number 3, you understand why that is?
Number 3.
Yep.
Because it goes from -3 to 1, right? So you
Yeah,
just
so the function we built goes from -3 to whatever x you just.
yeah. So it gave us 1, so we plug in v of 1. Is that correct? Okay.
Absolutely.
So the first one, So since it said typical cylinder, is that just the basic cylinder function? The volume of the
Yeah,
cylinder?
typical cylinder meaning it is a cylinder. It's not a cylinder with another cylinder removed. It's just a solid cylinder.
So would that be pi r squared h?
No, because so remember, you're just taking the rate of change. It basically, it's the area of the base.
Area of the base.
So remember, for our example, we did not integrate we did not integrate this third one with the heights multiplied by it. The rate of change is just all about the area of that the circular face.
Circular. Okay. So can you? So I'm sorry. Can you reword the first question like word by word? I mean, can you restate it
So
or read it off again?
if the radius of a typical cylinder is varying in the current delta x interval,
Typical cylinder.
Is varying in the current delta x interval, then the rate of change of volume of the cylinder is.
The rate of change of volume. Current. Okay. So that was. Okay, I guess. All right. Thank you so much.
Yeah, no problem.
Have a good day.
All right, you too. Thank you.
Thank you.